Hey everyone, good evening to all. Today I'm here to break down the results of my recent project on comparative analysis of brute force and divide and conquer in closest pair detection. Closest pair detection. Yeah, let me share my screen so that you can also see my project code. Just a minute. Yeah, I hope now you can see my screen. Yeah, in this project specifically, we took a deep dive into comparing two algorithms. The first algorithm is brute force method, and the second algorithm is divide and conquer approach. So here's a history of our methodology. We set up tests where each algorithm chewed through data sets ranging from 1,000 to 10,000. To keep things above board, we ran multiple trials for each set size to get an average runtime. The coordinates for these points weren't just pulled out of thin air, they were generated using a random number algorithm. To ensure each test was unique, we recorded the runtimes using Python's time ns function, and later switched those numbers to milliseconds for an easier read. Yeah, here you can see the coordinates x and y axis. After you can see the range of points from 1,000 to 10,000. Now here you can see the brute force approach code. This is the code to find them to in brute force edge method, and here it is divide and conquer method. Now let's talk about our results. Algorithm once runtime shot up as fast as we increase the number of points from 1,000 to 2,000. If, for example, take from 1,000 to 2,000 points, the runtime was almost tripled here. You can see here from 1,000 to 2,000, the runtime was tripled. By the time we hit 10,000 points, we are looking at runtimes just shy of 22,000 milliseconds. Uh, on the flip side, the algorithm two, the divide and conquer algorithm, was the tortoise to algorithms one here, but in the best way. Even at 10,000 points, its runtime was just over 82,000 milliseconds. After here we have plotted the graphs which shows clear picture. Now here we can see the graph one. Now let me zoom it up. Yeah. Here you can see the graph one showing algorithms on runtime skyrocketing compared to algorithms much gentler slope. Here graph two was all about algorithm one and empirical runtime. And steep curve wasn't surprising but did hammer home its inefficiency. Yeah. The graph three coming to the graph three. Graph three was where algorithm two really shine. This is the algorithm two, both representing algorithm two really shine. The empirical and predictive runtimes were practically holding hands. You can see it here. It's like holding hands, which tells us our theory was spot on. We also put this data in tables to get a more granular look. Here I will show you that one. Yeah, here you can see after running this code, you can get two table response. One table for algorithm one, the brute force method, and the other table is for algorithm two, divide and conquer method. To wrap this up, algorithms to divide and conquer strategy is without a doubt the way to go for the closest pair of points problem. It's more efficient and scales way better as the data sets get bigger. Our experiments back up the theory, and for any real world application, algorithm should be your pick. Yeah. Here you can see the ratio of the first algorithm, brute force algorithm. It's not that much stable compared to the ratio of algorithm 2, which is divide and conquer. Here you can see a stable ratio, almost stable, not that much, almost stable ratio. Here you get showing that it was consistent and predictable. So finally, the best approach is the divide and conquer algorithm for to solve closest pair of points problem. That's algorithm 2. Thanks for tuning in. Okay, bye.